Now, he's the physics teacher that's a new sensation. Just before you know it, he'll be sweeping the nation. Ain't no virus gonna stop your education, so don't be slipping, cause this ain't no vacation. Welcome back, physics fans. Yesterday we talked about work. We're gonna move on now today and talk about working energy. But first thing, I had one student that asked, could we do an example problem from yesterday? I'd be glad to. So if you'll get out those problems from yesterday, we'll look at one of those. How about number 8, the one that I was discussing that was I said it was a cannonball rolling down a hill. I was wrong. It was a mincemeat pie. The largest mincemeat pie ever created had a mass of 1.02 times 10 to the third kilograms, 1,020 kilograms. Suppose that pie with this mass slides down a ramp that's 18 meters and it's inclined with the ground 10 degrees. If the coefficient of kinetic friction is 0.13, what's the net work done on the pie during its descent? So the first thing I would do would be draw your free body diagram of the situation and identify all the forces acting on the mincemeat pie. So here we have our slope that the pie is on. Here we have the free body, the pie itself. We have the gravitational force pulling down on the pie, straight down, gravity. We have the normal force of the slope pushing back on the bottom of the pie. That's our normal force. And if it gave us mu, the coefficient of friction, then there must be friction in this problem as well. So we could go ahead and find the gravity acting on the pie, or the gravitational force. So that was 1,020 kilograms. 1,020 kilograms times 9.81. That gives us a weight of the pie of 10,006.2 newtons. 10,006.2 newtons. And if we do our little turny thing, then gravity is the only force that we have to resolve. So if we resolve gravity, the components of gravity would be straight downward in the vertical direction, so straight down onto the surface, and then parallel to the slope, pulling down the slope. And that's what I was talking about yesterday, about the x component of gravity being the only force pulling the pie down the slope, the only force doing positive work on the pie. And if that's a 10-degree angle, then it makes this upper degree 10 angle, because when we change our frame of reference, we're essentially rotating that slope 10 degrees counterclockwise, so that makes that a 10-degree angle. So we could resolve these two sides. If that's the adjacent and the opposite side, we'll do 10,006.2 times the cosine of 10. That gives us the y side, which is 9,854.2. I'll round up a little bit, 9,854.2 newtons for this y component of gravity straight down. And then if I do the opposite side, (10,006.2) times the sine of 10, that gives me 1737.6 if I round up a little bit, 1737.6 newtons. So that's the x component of gravity. So we know that much force is pulling the pie down the slope, but if you look at our free body diagram, there's also a force going in the opposite direction doing negative work, and that force going in the opposite direction would be friction. So it looks like we need to find the frictional force to add it into this problem. And if you recall, the formula for frictional force is mu times the normal force. Well, it gave us mu, the coefficient in the problem, is 0.13. Well, what's the normal force? The normal force pushing upward from the surface should be, or not should be, it is the same thing as the y component of gravity. If there's no motion in this direction, if all the motion is along the slope, then these two forces have to balance. According to Newton's first law, there can't be any motion in that direction, or change in motion, if it's not moving in that direction, or if it's not accelerating in that direction, I should say. So we know that the normal force has to be 9854.2 newtons also. So 9854.2 newtons. is the normal force. So if you multiply that together, 9854.2 newtons times the coefficient 0.3, I get 1,281.05. If I round up a little bit, 1,281.05 newtons. So that's the frictional force. 1,281.05 newtons. Now, in order to find net work, we talked about yesterday, you need to find the net force and multiply it by the displacement. So we said net force is, well, add them boys up, add them up. Take the sum of all of them that's causing the object to speed up, slow down, or change direction. So in this case, I'm going to call down the slope positive. So we have 1,737.6 newtons worth of force doing positive work, pulling it down the slope. The displacement and the force is in the same direction, minus 1,281.05 newtons friction going in the opposite direction, doing negative work. And we said that in our video yesterday, that friction always does negative work. It always opposes motion. So that's why it's a negative force. So we have 1737.6 minus 1281.05. And I get a net force of 456.55 newtons. Positive. Positive meaning that the sum of the two forces is a positive number. That means the net work is in the positive direction. That means it's accelerating down the slope, speeding up as it goes down the slope with that much net force. At that point, we could find the acceleration if we wanted to. You could simply take the net force, divide it by the mass, and find the acceleration, because Newton's second law, net force is mass times acceleration. But that's not what it's asking. It's asking, well, what is the net work? The net work would be the net force, 456.55 newtons, times the displacement. Net work is force times displacement, or net force times displacement. Well, it told us in the problem that it was an 18-meter slope. So 18 meters, there's your Newton meter, or your joule. So 456.55 times 18 gives you positive 8,217.9 joules. So there's your net work that's done on the mincemeat pie. So that required some knowledge from our force chapter to be able to answer that question, but it also required you to apply some new knowledge about net work also. So if you got that answer, congratulations, or somewhere close to that. Keep in mind I rounded off up here when I did my components. So if you were close to that, you did a great job. I had somebody email me some answers this morning, and they got the right answer. So that's awesome. So continue to work on those problems if you haven't. You have some more problems today on the work kinetic energy theorem, and that's what we're going to cover now. So if you want to pause the video and pull up the PowerPoint on work kinetic energy, we're on the slide where it says the work energy theorem kinetic energy. That's where we are. So I'm going to take a break, and I'm going to clean this board, and might take a drink of coffee. Where did my paper towel go? I found some shorts, that'll work. Okay, back. So if you remember the v squared kinematic equation, it should be on your note card with all the rest of your kinematic equations. So let me write that one on the board first. The one that is v squared. V squared is equal to initial velocity squared plus 2 times acceleration times, we said change in displacement, but we'll call it d for displacement. If the initial displacement is 0, then it would be d minus 0, so that's d. AP Physics students, if you're watching this, we showed you how that equation is derived algebraically from other kinematic equations. Honors and gifted physics, you took my word for it that equation works, and you used it numerous times, especially if you didn't have time in a problem. That was a good one to use to find final velocity or acceleration. What I'm going to do is I'm going to rearrange that equation to solve for acceleration. So a little algebra, not too hard. So I'm going to subtract this over here to get it to the other side. So we get final velocity squared minus initial velocity squared is 2AD. And if I divide by 2D here to cancel it out, and divide it over here, I end up with that right there is what acceleration is equal to. Acceleration is equal to final velocity squared minus initial velocity squared over 2D. So hopefully there's not a glare on that. You can see that okay. So that's what acceleration is in terms of that kinematic equation right there. So remember that, because we're going to use that in a minute. And that's what this first slide says, is that the net force acting on an object causes the object to accelerate, changing its velocity, and it gives you that equation right there. And unless you read the textbook like you were supposed to, then the PowerPoint doesn't tell you how it got to that point. So that's where we are right there at that point. Now we're going to do some more algebraic substitution. So let's go back to the work formula, or the net work formula. If you recall from yesterday that net work equals net force times displacement. So the same formula that we used in that mincemeat pie problem to find the net work. We added up the two forces to find the net force, multiplied it by 18 meters to get the net work. Well, from Newton's second law, and I said this earlier, what is net force equal to? Well, net force is equal to ma, mass times acceleration. So can I substitute ma in here for net force? Well, sure, that's just algebraic substitution. So instead of net force, I'm going to define net force as ma times d. And what do we get? We get work equals mad. Work makes you mad. Yeah? No, not really. Doesn't make me mad. I'm having fun. But so net work is equal to mad, or mass times acceleration times displacement. Well, once again, what do we define acceleration as using that equation? As this right here, the final velocity squared minus initial velocity squared all over 2d. Can we plug that in for acceleration? Well, that's legal in most states to substitute that also. So mass times acceleration. Well, what's acceleration? It's all of that. V squared minus initial velocity squared over 2d. All of that, if that's acceleration, still times d. So mass times acceleration times displacement. Well, let's do some canceling, and let's do some distributing and see what we come up with. If we got a d here, which is essentially d over 1, and we got a d in the denominator there, those will cancel out. That's not 2 d's. That's not d squared, having two separate d's. That's just the number 2 times d. So d will cancel out. We get rid of that. Then let's distribute m in our equation. I'm going to rewrite this. Net work is equal to mass times v squared over 2 minus mass times initial velocity squared over 2. So all I did was multiply through by m and divide this into two separate equations, variables. I don't know. Math teachers are probably beating me up if I don't know what to call that. And anytime you have something over 2, it's really like saying 1/2 times that. So if I rewrite this one more time, I get net work is equal to 1/2 m final velocity squared minus 1/2 m initial velocity squared. Well, that's a new equation there that you've never seen, but what we just derived is kinetic energy. this right here is final kinetic energy, we'll just call it K, and minus this right here is initial kinetic energy. I'll rewrite that at the top because I know that's hard to see at the bottom down there. So let me get some space up here. So what I just derived was this equation here, that net work is equal to 1/2 m final velocity squared minus 1/2 m initial velocity squared. So this is kinetic energy. So if you go to, actually jump 2 slides over, because the next slide just shows you exactly what I did in deriving that. It doesn't tell you really well how it was derived, but it is. But the next slide is kinetic energy is therefore defined as 1/2 mv squared. So this is final kinetic energy, as I just said, final kinetic energy minus initial kinetic energy. So the SI unit for kinetic energy, it says on that slide, is a joule. Do you think that's a coincidence that kinetic energy is measured in joules just as work is measured in joules? Well, I think not. If the two are set equal to each other, that the amount of net work done on an object equals the change in kinetic energy of an object, well, joules are equal to joules. That much net work in joules is equal to that much change in kinetic energy in joules. So, like I said yesterday, work is really what bridges together forces and energy. So we used the force equation here and kinematics to derive the relationship to change in kinetic energy. So this is called the work kinetic energy theorem, that it says right here that the net work on an object changes an object's kinetic energy. So that means there has to be a net force, an unbalanced force, acting through a displacement for the kinetic energy of an object to change. Keep in mind, if the net work is 0, if all the forces balance, then the object's kinetic energy does not change. It either stays at rest with no velocity, or its velocity is constant. It doesn't speed up, slow down, or change direction if the forces are balanced. So if this is 0 over here, net force times displacement is 0, just like me pushing on the cabinets yesterday. I had no work done, no net work done. Well, the cabinet's kinetic energy didn't change. It didn't start from rest and start accelerating forward. It didn't do it. However, I said yesterday, if I pushed on my coffee cup, even with a small force and moved it a millimeter, then there was an unbalanced force acting on it, and it caused the kinetic energy of that coffee cup to change. It went from an initial velocity of 0, rest, to some final velocity as it moved through that displacement, 1 millimeter. So I told you it gets a little harder because, once again, as I said yesterday, you can see forces, you can see displacements, you can measure those easily, displacements with a meter stick or whatnot. This is kind of hard to see, a change in energy. How does it go? Well, if you think about it in kinematics terms or in force terms, it's really just a mass. Mass doesn't change usually for an object. Well, the velocity can change if and only if there's a net force acting through a displacement. So this is kind of the short version of the work kinetic energy, that net work is equal to delta K. Once again, delta in math meaning change in. So this is kind of the abbreviated version of the work kinetic energy theorem, that net work is equal to the change in kinetic energy, final minus initial kinetic energy. If you wanted to do the more expanded version, then what is net work? Well, it's net force times displacement. What is change in kinetic energy? Well, it's 1/2 mv squared final velocity squared minus 1/2 m initial velocity squared. So this is the short version, this is the longer version. So it kind of depends on what you're looking for in a problem. Some problems you may be only looking for the net work, or it gives you the net work. Some problems you may be looking for the final or the initial velocity. So both of these are the same formula, it just depends on what the problem says. So unlike yesterday when I didn't do an example problem, how about we do an example problem from the ones that I gave you to do over work kinetic energy theorem. I gave you the even numbered problem. I gave you the odd numbered problems to do on this next handout, but I'm going to do an even numbered problem one. So if you get up that handout, if you have it, I have it somewhere printed out, and here it is. Look at number 4. Number 4 is the ones of Hans Liebold of Germany. It says he drove a race car 12.6 kilometers. Now, you might think, 12.6 kilometers, there's the displacement that he drove in this problem. Not really. We'll see. It says he drove that distance or displacement with an average speed of 404 kilometers per hour. Suppose he applied the brakes to reduce his speed. Well, it doesn't tell us where he applied the brakes. It could have been in the middle of the race, could have been at the end of the race. Well, we don't know. So that 12.6 kilometers is really not part of the problem. But it says, what was the car's final speed if -3 megajoules of work was done by the brakes? Assume the combined mass of the car and driver to be 1,000 kilograms, or 1 times 10 to the third kilograms. So what does it give us? Well, it gives us the net work done on the car right off the bat. We don't need to find the force or the displacement that those brakes act through. It says that the brakes do -3 megajoules of work on the car. Well, does that make sense? Well, if we make our velocities positive, if we make them going in the positive direction, doesn't it require a negative force to slow the car down? And if it's a negative force, then that's negative net work. So we should get a final answer for our final velocity that's less than his initial velocity. And we'll see if we do. If we don't, then we made a mistake somewhere. So net work, it gave us right off the bat, was -3 megajoules. Remember yesterday I said 1 megajoule is 1,000,000 joules, so -3 would be -3 million joules. So there's -3 million joules. Let me put a unit in there, joules. What else are we given? Well, it told us the total mass of the driver in the car was 1,000 kilograms. We want to know the final velocity, but it gave us his initial velocity. It said he was going 404 kilometers per hour. So 404 kilometers per hour, remember that's not a standard unit, so we want to convert that into standard units, meters per second. So 404 times 1,000 divided by 3,600, that converts it to meters. We get 112.22 meters per second. So his initial velocity, what he was initially going at before he hit the brakes, was 112.22 meters per second. So let's plug in what we know. 1/2 times 1,000 kilograms times v squared, that's what we don't know, final velocity, how fast was he going afterward, minus 1/2 times 1,000 kilograms times 112.2 meters per second squared. So if you've forgotten to convert there, then you would have gotten a wrong answer. You had kilometers per hour there and kilograms and joules, and your answer wouldn't have come out correct because your units didn't cancel correctly. So I'm going to go ahead and, well, I can do this in my head, that -3 million is equal to 500 v squared, half of 1,000 is 500, minus, I'm going to go ahead and get a number there. I like numbers. So half of 1,000 is still 500. 500 times 112.2 squared, and I get 6,294,420 over there, and that would be in joules because that's a initial kinetic energy. His initial kinetic energy was 6,294,420 joules. I'm going to add that to the other side in order to cancel it out there. Keep in mind that's a negative number. So I get positive over here now, positive 303,294,420 joules is equal to 500 final velocity squared v squared. I'm going to divide by 500 over to the other side, and I get 6,588.84 is equal to v squared, so that canceled. And then all I got to do is take the square root of both sides to find my answer, and I get 81.17 meters per second positive. Okay, well, let's see if that makes sense. He was initially going at 112.2 meters per second in the positive direction, because I made that a positive number, and negative 3 million joules of work was done on him to slow him down, so his final velocity over here somewhere was 81.17 meters per second, still going in the positive direction. So physically, that makes sense. The only mistake I could have made is if I would have done a math error somewhere along the way. I know these numbers are right that I plugged in there, so from here down is just math. I know that's the right answer because I checked it to make sure. Didn't want to make a mistake and give y'all a wrong answer, but so that's the correct answer. Initial velocity 112.2 meters per second. Final velocity after that much work was done was 81.17 meters per second. So that's an example of a work kinetic energy problem, that the amount of net work done on an object changes its kinetic energy. So that's the work kinetic energy theorem. Next, we'll be doing some conservation of energy, which is a pretty deep subject. Conservation of energy is, because you have both forces that are conservative, those that allow you to conserve energy, and forces that are non-conservative, ones that where you lose energy to the environment. The energy is not conserved, or I should say mechanical energy is not conserved. All energy is conserved, but mechanical energy is not conserved sometimes, or pretty much all the time. So I'm gonna do that video, and in that video is going to be power also. So you have some problems on power that you're supposed to do. Power is a pretty easy subject. I did not give you any problems on conservation of energy, because if we were in class and we were face to face and I could come check your problems and help you out, I would have given you some conservation of energy problems. But it's very important. So that's why I need to cover it. But I didn't give you any problems to do over that. So tomorrow, I actually have to go to Athens tomorrow to get Brett's stuff out of his dorm. University of Georgia gave us like 2 weeks to do that. So I actually took a day off from school. And so I will post the video on conservation of energy and power tonight. I'm going to have it before tomorrow posted, so that way you'll have it to look over tomorrow. But just like I said yesterday, I hope you all are keeping yourself inside for the most part. I hope you're staying safe, staying away from large crowds of people. Hopefully you weren't on that beach picture that I saw on the news where it said St. Simon's Island and there was lots of students on the beach. Hopefully that was not you. You were home doing your physics work. So y'all keep safe, keep your families safe, especially those that are elderly, your grandparents and maybe even your great-grandparents and aunts and uncles. So I hope to see you soon. Don't know how long this is going to be. We know it's going to be at least until after spring break, but hopefully I get to see you then. But I'll keep plugging along and keep teaching you lessons as long as I need to, because I want you to stay educated. I want you to learn physics, because as I say all the time, physics is the most important subject you're going to take in school, because it's everywhere. It's everything you do every day of the week is physics. So y'all take care, and I'll talk to you again soon.